So the last time we looked at the Game Boy Advance, we were looking at how the buttons worked. We then modelled up the buttons on a breadboard. So we have the equivalent of what's happening on a Game Boy Advance button system now, where we press these buttons and it goes from a high 3.3 volts to a low ground signal. The point of this is we're going to be making an open source LED project, and we're going to try and finish most of it in this video. So it's a pretty simple project. We could just wire LEDs straight to power and have them light up on the board. That's what most people do, and there's not really much use, there's no fun in it, there's no point me open sourcing a design that's so basic. So we're going to do a design that uses a MCU to have full rainbow effect LEDs, where you can have modes like candle modes, flickers, changing each button's colour and brightness individually. But we'll do that after. First, I want to get you into electronics and hardware a little bit easier. So we've done the shape already in Inkscape of the button boards, so we have the PCB shape ready. We've modelled up how the buttons work, so we can now prototype the design on a breadboard to prove it before we go to manufacture. And what we're going to do next is make it so that when we hold these two buttons, which I'm thinking will be start and select, when we hold them for say 2 seconds, it turns the lights on. And when we hold them again for 2 seconds, it turns the lights off. So at least those that install LED mods and the basic LED mods, they have the option to enable and disable the lights without them having to be physically removed. So this is a fairly simple circuit, but it's nice because it uses a few basic principles, and I get to show you how resistors, capacitors, logic gates, flip-flops, and other kinds of electronics work, as well as make it into a little bit of a fun project. So let's just jump in now and take these two button presses, which are instantaneous lows, and convert them to slow 2-second presses that then convert to an on-off signal that then drive a single LED. We'll try and do this in all one sitting, so we can then get to making the board in one more video and get it into production. So let's just jump in. So we have here the buttons, if you remember, and we have the 3 volt input here that we send in, with the buttons pulled up high, and then the outputs here that will read low when pressed. So the next step is we need to take those two low inputs and convert them to a single output that is high when both buttons are low. So for that we need to use a logic gate. There are various types, and let me just bring up the types now. So you can see here we've got NOT gates, AND gates, NAND gates, ORs, NORs, XORs, and exclusive NOT ORs. These are all logic gates. They're used in programming as well as hardware, and it's what forms typical electronic circuits. So most FPGAs, most chips, most things that have any kind of logic work on these logic gates. You can see you've got B and A for most inputs, and they're the two types of inputs. You can have more than two, and the truth table simply expands in a similar way. But we're going to be working with a 2-input NOR gate in our case. As you can see, the NOR gate, when the inputs B and A are both 0, the output X is 1, which is high, which is what we want. And in all other instances, whenever it's 0s or 1s mixed or both 1s, the output's always 0. So the NOR gate in this instance is what we want. We want, when both of our buttons are low, for the output to go high. No other gate gives you that output. An OR gate would give you the inverse logic, where it's only low when both are low, but in this case we want a high logic. So the NOR gate is what we're going to use. The NOR gate we're going to use is this one here. I've just found basically a generic one for this example. There's millions out there, but this is just one we want to use. The only catch here, as you'll notice, the logic symbols here have this little trigger symbol here. This little symbol. And if we go to the logic gates here, there's no such symbol. What this is a Schmitt trigger. And it's basically hysteresis between the inputs. You can see here it says with Schmitt trigger inputs. The reason we need this, and it's something I'll do a video on at a later point, is that because we want to hold the buttons down and not necessarily just have a fast input, we're going to slow these inputs down in a moment to get a slow rise of voltage. Whenever you've got a slow rise in voltage, it's recommended to use Schmitt triggers. Otherwise, during the transition between the high and low point on the curve, if it's going up slowly, the circuit can rapidly change between high, low, high, low, high, low, and that's what will happen. So because we're going to slow the inputs down to these input gates, we need to have Schmitt trigger logic. So don't worry too much about what that means at the minute, so long as you use a Schmitt trigger for this, and I will explain it more in depth when we use them again in other circuits. So in terms of this circuit, we just zoom in. you can see that this is the chip, and if I show you the actual chip, we have the chip here. So this fits nicely into the breadboard. You can see the writing on it there, upside down, but that's the chip make 7002, and that's the data we have here. So on this board, this will be the way up, and pin 1 will start here and go down, and then go across and then go up. So it's an anti-clockwise pin layout. If we look at the data sheet, you can see that we have pin 1 here at the top, going down, around and up. So this is the circuit we're looking at. Now, this has got 4 NOR gates in, we only want 1. This is just how chips are mostly made, because you rarely need just 1. They tend to come in packages of 4 as a common theme. We only really care about number 1, so you can ignore all the pins on number 2, number 3, number 4. So the whole right side of the chip we don't care about, except the power pin at the top, which will provide power to, and the ground at the bottom left, and then the top 3 pins here. So it's a really simple circuit. We're going to put A and B in from the buttons, and Y should come out as 1 when both buttons are pressed. So it's a really easy circuit to wire up. So let's just get this circuit now. Let's just place in the chip. When the chips are new as well, they tend to have the legs spread a little wider. And bear in mind, this is already used here, this row, so it won't come a few down. We probably want to be around here. And then you can put it in one side. So as the chip's going in one side, you can then gently push down the other side and use your finger to, basically rub the pins into the holes. Once they're in, just push down and lock it in. So that's our circuit there. So if we just pull up the data sheet side by side now, so it's nice and easy to see, you can see that what we need is this top pin is one of these inputs, and the bottom pin is the other input. So we want to simply bridge these. We could bridge them over here to bring them over, and then bridge them down to keep the circuit neat. So we just get a blue and jump it over. There's 1. There's 2. And I add a grey to input 2. Like so. What we now have is the top button comes down this blue wire across, goes to input 2, and the bottom button goes to input 1. So there's input 1 and 2. These go into the chip. Now, before we forget, let's just wire up the power rails. So we want the bottom left to go to ground, and ground on ours is this outer blue one. So for that, we go from ground to the bottom pin. And power at the top right. So that's the outer red line again. And at the minute, our board doesn't technically have the power that side, it's all this side. But we can just bridge over. So we'll just go to, like, say, the bottom and bridge the power over here. So let's just take a wire and say bridge from here to here. Just so we have the powers joined so we can use both sides of the rail. And we might as well do the same for the negative. Let's just bring them over. So now we've joined both rails to be the same. So now we can wire the top right to the power input. So there we go. Now the chip has power coming in, ground going out, 2 inputs, and now we should be able to monitor this output. So we're going to monitor that output on the scope, and let's just check the circuit's working at this point, which it should be. It's nice and easy. Let's get power of 3 volts to this circuit. We'll just connect our bench power supply at 3 volts at the minute. I will make a little breakout board on this to give us some battery power so we don't have to have the bench running when we're doing these things. Now we've got that, we'll bring the oscilloscope in. The oscilloscope needs a ground lead. So simplest thing for that is you can just get another jumper wire, connect it to say ground over here, and just grip your ground probe of your oscilloscope on, and now we are free to probe around. So the first step I'd do is check we have power. So there you can see we've got power. It's a bit noisy because we have no capacitors on this circuit anywhere to smooth anything. There's long wires, so this kind of noise is expected on a breadboard. It's also good to test on a breadboard in a way because it purposely shows you the noise. And if your system works when there's lots of noise, it's certainly going to work when it's smoothed. You can see if we just add a capacitor to the positive and negative rails, it reduces that noise a little bit, but nothing massive. So there's the noise back. So for now, we'll just run bare and see if it can cope. The buttons here are pulled high, as we mentioned, and pressing them pulls them low. Let's check they make it all the way to this chip. So top of this chip here should be this bottom button here, number 1. And there we go, it's got the input. And the one below it should be the button above. So there we have the inputs. So now the moment of truth is, does this third output work? So should output high when both are pressed. And there you go. So you got 1 press does nothing, 2 press does nothing. Both press goes high. So this circuit's now doing what we want with one exception. It's not slow. So the minute we'd press start and select together, it would trigger our circuit. So in order to solve that, all we're going to do is use an RC filter. And all an RC filter is a resistor and capacitor. Now, instead of sending the wire straight down here to connect to the input of the NOR gate, what we're going to do is just remove this one, say. And for an RC filter, if you put a resistor from the input to the output, like this. So we've just replaced that wire with, just move it over a little bit so we can see. We've replaced the direct connection through a resistor. This resistor will limit the current going into the circuit. Now, in order to slow down that rise, as in the power comes through the switch, goes through this resistor and into here and instantly rises the voltage. If we simply put a capacitor connected to the input side of the NOR gate, so this side of the resistor, which is important because above here will slow the signal up here and not necessarily down here. So you want the positive. If we just get a 10 microfarad capacitor, and the ground in this case is where the stripe is, connect the ground to the ground rail and the positive to the input side of the NOR gate. If we now probe the input to the NOR gate, which is here, and we press a button, see how it slowly falls? So you press it and it's slow to fall. We can calculate the time something takes to rise. If you just simply search for resistor capacitor charge time, you can get a graph like this. And if we enter the input voltage of 3, the capacitor I just used is 10 microfarad, and I've got 180,000, so 180k resistor. If we calculate this, you can see the rise time here says it takes 1.8 seconds to charge up to 4 RC. So practically full. Now, the system will trigger a low voltage when it's below about 2/3. So this time will be a bit less than what it's stated because it will trigger sooner rather than later. And in our case, the system is slow to change both directions. So it's slow to change when pressing and slow to rise when releasing, because the same thing happens in an RC filter both ways. Again, don't worry too much about RC filters. I will teach these separately. But for now, what we have here is a 180k resistor with a capacitor. And what we basically have is this setup here. So we have the voltage in, resistor here, and then the capacitor to ground. And this V out point here is the point that will be slow to rise. The basic reason is a resistor is the resistor. If you put two resistors in a setup where they are one side positive and then going through to ground, the middle point will be a percentage of the original input voltage. Capacitors, when initially given power, act like a dead short in effect. It acts like a 0 ohm resistor. But over time, as energy comes into the capacitor's resistance increases, and therefore the volts drop over it increases, and therefore the voltage rises. Again, don't worry too much about the in-depth knowledge of this for now. Just know that this is an RC filter, and when we place a resistor in line and a capacitor to take away the current as it's charging, you'll get a slow rising signal. So as we can see on here, the signal here now when we press the button is a slow fall. If we were to just remove this capacitor, it would now fall instant. And if we were to install a smaller capacitor, say a 1 microfarad, then now the button press should be a lot faster. So you can see now the rise and fall time is a lot quicker. So now we have that one done, let's just do it on the other button as well. So we have 2 slow rising pins for both. If you want these resistors and capacitors and ICs and wires and everything, this entire lot of parts is sold on our website, retro6.co.uk. The whole point of it is it allows you to follow along and build these circuits yourself so you can learn from them. So I do encourage you always to try to build these things as well, because that's the way you'll learn. You only learn so much by watching, and then you'll learn the rest by actually doing. So we have a resistor and a capacitor RC filter here. And let's put another RC filter here. And now let's test both inputs. So input 1 at the top here is a slow fall. Input 2 for the bottom is a slow fall. So that now works. So now the key question is, do we have a slow press where this turns on after a few seconds? And look at that, perfect. So we have not only a slow press, which will then trigger on. When we release, it will hold for a second or two as well. And what that will help with is, say we're turning the system on and off and we hold for a few seconds and it goes on, then we let go and press again quick. It's not going to re-trigger by mistake. It's going to stay in the high state, which will help. So now we have a circuit here where the buttons come in, 2 inputs come in, we slow them down through RC filters, and then we gnaw them so that we get a single output high whenever we've held these buttons down for so long and let go. So what's next after that? Well, next is, we've done this, so now we can get rid of this schematic, and we can come to this. This is a DType flip-flop. So this is a semiconductor, and the point of a DType flip-flop, there are many ways you can use it. One good way is every time there's a high pulse signal, we toggle an output high or low. So in essence, every time we get a high from our button press output, it will then output either high or low each time we press it. So every time there's a high pulse, we want the output to change to a low, and if it's already in a low, it wants to go high. If it's already high, it wants to go low. D-type flip-flops can be used in many ways. You can see there's all different circuits. There's, again, logic gates here. So this is kind of the truth table or the function table. We're going to ignore these presets and clears. These are extra pins we don't need. We have a clock and a data pin. And the basic rule, if we look here, every time there's a high clock pulse, then the data is high, then the outputs, which are called Q. So let's ignore Q not for now. That's basically the invert all the time. So whenever this is high, this is low. Whenever this is low, this is high. That's all Q not is. It's the inverted Q. So all we need to focus on is clock, data, and Q. So the only thing we're interested in is every time the clock goes high, what happens? We're going to keep these high anyway. So we're going to pull these 2 pins here high. So literally the only part we care about is these 2 lines. When the clock goes high and the data pin is high, then the output here will be high. If the clock then goes high when the data pin is low, the output's low. So in essence, all it does is you can put any data on this data pin at any point in time, but when you then send a high pulse to the clock, it will transfer over to Q. So it's like a latching circuit. So whatever's on data at the moment in time that clock goes high, Q will then take on that state. The minute you drop the clock, the data is no longer matching Q. So you could pulse high while data's high and Q will go high, and then you can drop the clock and you can change data all you like and Q won't change. So we're going to use this in a configuration where the clock in this instance is our input from our button press. So this will go high after 2 seconds. Now, what do we do in order to turn the D flip-flop into a toggle switch? Well, what we have to do is, if you look at the not Q, in effect the opposite of Q, if we say at the point in time of the clock going high, what do we want on data? We want it to be the opposite of what Q currently is. So if we tie the data line to the not Q, and say Q is high at the minute, meaning Q is low on the Q not line. If we tie Q not to data, it means when the clock rises, the data pin will be low, and so it will invert Q every time we press it. Again, this might be a bit complicated to understand, but let's just see it in action and I'm sure you'll understand. So let's take firstly this output of this system before we forget, which was the 3rd pin down, and let's just bring that output down further so we can do something with the output. Let's actually bring that a bit further down and then we could probably go straight to the chip input itself. You can see again we have a chip with 2 inputs, or rather 2 systems, so 2 flip-flops in one. We don't care about this right side at all, except again for the power pin, and we're only concerned with the left side, so it's got 2 of these chips in one. So let's just first tie the output here. Down here. And let's see if this input wants to be our clock, which is the 3rd pin down on the chip. So let's just get the D flip-flop and see if we can tie this in to be the 3rd pin down. Yes, we can. So if we place it here, you will see now, we just focus on this area, we have the 3rd pin down being the input from the output of this NOR gate. Let's get the power rails in again. So this chip wants ground on the bottom one, which is here. And it wants power on the top right. And you'll find a lot of chip series follow the same kind of pin layout fairly commonly. So there, it's got power and ground now. So what do we care about next? Well, as we saw, we have pin 1 and pin 4. So this clear and reset pins are special functions where when you set them low, because they're active low with the bar across the top, as you see in the diagram up there, it means when they go low, they're active. Well, we don't care about them for now, so let's not even bother thinking about them. What I'm going to do is just pull them high through a resistor to disable them, just keep them in a high state. So if we go to the input rail and pull pin 1 high, and this is just a 47k resistor. Anything for this demo, anything for kind of your prototyping doesn't really matter, you're still going to pull it high. Anything above 1k is fine. When we come to the final circuit, the higher the value, the less power the system will draw. So between 47k and 500,000 tend to be where you use pull-up resistors. We'll get another 47k resistor. We'll go on pin 4 and we'll pull that high as well. And then we can always get the scope to confirm as we're going. So we can just probe this pin is high, which it is. This pin is high, which it is. And the current input to clock, when we hold the buttons down, goes high, and when we let go it drops. So far we're good. So now what's left? We don't care about all of this side of the circuit. We want the data, as we mentioned, the data pin here, which is what will get set to Q whenever the clock's pulsed. We want to just tie that to Q naught. So if we just look at the minute at what the system's doing, we can see Q naught, we can see Q here is low, so Q naught should be high. So basically, no matter what state the system's in, whatever this pin is on Q, this one below will always be inverted, because it's just using an inverter inside. data at the minute is low. So you can see data's low, Q's low, not Q is high. If we tie the Q not to the data line, so that will be pin 6 to pin 2, like so, we can see that Q not is at the minute, Q's high, Q not's low, and so when we put a clock pulse on by pressing the buttons, this Q, which is high at the minute because it's just floating around, should be latched to the data pin, which is the exact opposite. So what should happen is Q becomes whatever D is, and because we've tied D and Q not together, Q becomes the exact opposite of Q every time there's a pulse. So if we were to now hold the buttons down for 2 seconds, you can see it's flipped. I've let go of the buttons and it stayed the same. So what we have now is a toggle circuit. So I'm on Q at the minute, and if I hold the buttons down, it toggles. I let go, it doesn't do anything because it does nothing on the falling edge of the clock, only the rising. So we hold, toggle. So we're off, hold again, we're on, hold again, we're off. So we've just, with a very simple circuit, created what we finally need, which is a simple toggle on and off by holding buttons for a few seconds. Now all that's left to do is take that output of Q, which is the on and off, and drive the LEDs on and off. To do that, we just use a transistor. But just for quickness, if we look at the data sheet on this D flip-flop, you'll find that the current supply of Q, which we should find in the recommended operating conditions somewhere, high level output current and low level, so sourcing and sinking. You can see we can source and sink between, if we're providing 5 volts, it would be 8 milliamps. In this case, it can source and sink 4 milliamps. So we have current limiting on this chip. So what that means is we can safely just tie an LED straight to the output, because the LED is going to have a current limit through this chip, so there's no need to put a resistor on. So for this test, let's just put the LED to ground and one pad to Q. And now if we hold, you can see the light come on, hold again, light goes off. So this is in essence our LED circuit. So we just hold, light comes on, hold, light goes off. Oh, I didn't let go long enough. Hold, light goes off. Now, because this is just 4 milliamps, we will obviously pass this through a transistor and then drive many LEDs. But that will do in the schematic setup when we come to do the actual circuit board design next. So there's no point showing you a transistor. I can show you that on the schematic, and we could always jump back on the breadboard to show you the transistor. But you're going to get the exact same effect here. You basically take a transistor, tie one leg to ground, the LEDs start at the other side of the transistor, and the trigger, the third pin, is simply this pin here. So there's nothing really to show you there. But there's our circuit, on and off. And again, if you press too fast because of the RC circuit being both ways, it won't turn off. And that's it. So next step is to get this on a schematic, design the PCB, chuck in the transistors, and order the board. So without further ado, let's jump into that next.